transform model queries values of keys in the self-attention and in the feed-forward memories. Feed-forward self-attention and key-value post is today. Have you forgotten about transformer feed-forward layer as me? It actually eats 2/3 of the parameters of the model, so it's super important, except I actually haven't focused on it too much. So this post is about it. In the last post, in the last video, well, that was on the Lambda network, it sketched self-attention as a differentiable query key-value store. And this post is more about this idea. It expands on that using 2 papers. And it describes feed-forward sublayer as a similar to the self-attention, again as some sort of key-value querying, except in the feed-forward layer, the keys and values are constants. So get ready for a great juice of 2 papers. Also, if you'd like more like this, you can subscribe on the YouTube or by mail on my blog, waclawkosar.com. So can we gain more understanding of the transform model by looking at a feed-forward layer as well? And what is this key-value store? Where is feed-forward layer? So if you look at the one encoder layer, we find that there are 2 sublayers followed by residual connection and normalization. So first we have this attention layer, and then we have the feed-forward layer. So the feed-forward camps within the encoder and decoder layers after the attention sublayer. What is feed-forward layer exactly? Do you know? Well, the feed-forward layer is position-wise transformation, whereas self-attention is on the whole sequence, all positions. And feed-forward layer consists of following operations of linear transformation, ReLU, and another linear transformation. If you want to see equation, you can look over here. So we have a matrix applied to queries, then we have a bias term. To that, we apply ReLU, and to the results of ReLU, we apply another linear operation via matrix with values, and we add another bias term. What is the difference between key-value memory and the feed-forward layer? Have you noticed that feed-forward sublayer is akin to key-value memory except for non-linearity in the ReLU and the bias term? Well, it is very similar. If you look at the definition of key-value memory, that at least one paper sort of described it in this way, we have this softmax applied to match of match of queries and keys, and then we apply values to the result of the softmax. So this is very similar to previous, right? We only have a difference in the ReLU, non-linearity, and the bias terms are not present in the key value. Also, this is very similar to the attention, right? Except in the attention, the keys and values depend on the input, and they have dimension of L. So if we look at the first picture in this post, we can see the dimensions here. So we have a query that depends on the input. To that, we apply keys that has dimension M instead of L. We add bias term, and then to the result of ReLU, we apply value and add a bias term. And this part, the keys and values, are trained, but they are constants in prediction, and only the query depends on input. In self-attention, this part, the keys and values, have different dimension. Instead of M, there is L, and there are no bias terms, and instead of ReLU, we have a softmax. So we have the similarity. Feed-forward layer is like key-value memory, and that is like self-attention. So if it's so similar, why nobody tried to replace the feed-forward sublayer with just some addition to the self-attention? Well, somebody did restate the feed-forward layer as a key value memory and incorporated it into self-attention sublayer. And they slightly outperformed the vanilla model on the next token prediction task, actually. But does the feed-forward sublayer really behave like a key-value memory, or just talks to talk? Well, there's this paper, Transformer Feed-Forward Layers Are Key-Value Memories. It's a very recent paper, where the authors show that the feed-forward layer experimentally does behave a little bit like a key-value store. So they study activation of feed-forward keys for the last position in the input sequence. The activated keys there are keys defined as a top n keys, with the top n ReLU outputs for a given feed-forward sublayer for the last position of the input sequence. For the most of the keys, feed-forward sublayers, the authors found one or more human-interpretable input text patterns for which the key was being activated. So for each key, they found some kind of text patterns which ranged from single last word matches to more complex sort of topic-oriented patterns, like one of, part of, and among. They also observed that the upper layers memorize more abstract patterns, which makes sense because the self-attention is able to do more work in the upper layers. Unfortunately, not all samples were provided in the preprint, so I was not able to fully validate the claims. And what's a little bit strange here is that they describe that they have multiple patterns per key. So, but do those patterns actually involve a single topic or disparate topics? If they involve disparate topics, is it okay still speak about memory cell, right? But individual activated values were tended to predict next output tokens of the entire model, but only in the higher layers. In the lower layers, you would expect, right, that the model is still working on the prediction. So, but it seems that the correlation in the higher layers is increases. Sort of makes sense. What's interesting that they typically observed that tens of memories were activated and then aggregated, and that the model output vector differed from all single memory prediction most of the time, but in some 32% it did match. So that seems those were some sort of very easy patterns, like very common stop words and so on. But otherwise, the residual connections and memory outputs seemed to disagree mostly. Disagree sort of between each other and between the residual outputs. So that would mean that the feed-forward layer sort of works like a correction in some ways, as a correction function that sort of corrects the residual connections while being added to them, and sort of refines through layer to layer what is going to be predicted. All right, so last post was about LambdaNet work. And I spoke a lot about these positional embeddings. Are they similar to the transformer feed-forward layer? So the positional embeddings actually are something between self-attention and feed-forward layer. They are also about querying, some sort of patterns and value store. But the keys, are also constants in the feed-forward layer. But in what's different Okay, so difference between lambda-net positional embeddings and feed-forward layer is that the values were dependent on the input in the lambda network, whereas in the self-attention, everything is all query key value depends on the input, but in lambda-net that's not the case. In lambda-net, keys do not depend on the input. So lambda-net keys depend on the input, queries, lambda-net keys do not depend on the input, but the query and value does. In transformer feed-forward layer, queries depend on the input, but the keys and values do not. In self-attention, query, key, and value all depend on the input. Okay, I hope you got the idea of the two papers mentioned. You can check out the post.